Welcome, everyone. I hope you will enjoy this presentation. It's this platform for consumer flexibility is something that has been developed over several years here in Lund, at south of Sweden, together with Noda and Kraftringen and several other parties. So we are doing something that we call total optimization and AI for consumer flexibility. So here are a little bit about the topics that we will cover. So first we will start to explain this total optimization sector coupling. Then we will go into the actual platforms and the different types of usage of these different types of flexibilities. And then we will also present another user case from Gothenburg, also in Sweden. So eFlex is in Kraftringen in south of Sweden, and Flexus is in Gothenburg in middle to southwest. And then and a little bit about replication and next steps of these solutions also. So when we talk about the future energy ecosystems and total optimization, we have seen the last years that there is an increased need of sector coupling, and the production optimization plant can not only be isolated, this type of silo thinking that have been before, but nowadays all of these things in the energy systems have to kind of be part of the total optimization. It could be waste heat from nearby industries or server halls. It could also be large heat pumps in the system. Of course, there can be new techniques such as CSS or CCU. Hydrogen can also be part of the system, somehow connected. And there can be solar plants, wind power farms connected to batteries, and then vehicle to grid, hydropower, and then also very important now, the building side as well. And all of this have to be taken into consideration while you fulfill the demand and you optimize the heat network, but also take into consideration the trading planning, because the trading markets are also an important part of increasing the profitability for the energy companies. So having this type of optimization system can help then to lower production costs and emissions. And if you also connect the consumer flexibility side, you not only lower the energy use in the buildings, but you also can lower these costs and emissions even more. That was proven as results of this 5-year project. So this project we decided to call eFlex, that was then developed in Lund. And as you can see, there were several different partners, university, research, and the region of Skåne, and then the energy company, and Noda was also part of this. And we decided to develop this digital platform. And the goal was to create a more robust, environmentally friendly, and economically optimized energy system. And this required new business models towards the building side, dynamic pricing models to incentivize this behavioral change. And we needed this total optimization where the buildings were part of the optimization for the energy company to use at certain hours. And this need was for district heating, cooling, heat pumps, and electricity. So we did a pilot on several different test objects in Lund and Eslöv, close to Lund. And a requirement was also that it would be a replicable and scalable solution. Sorry. And then we were also using AI. The Noda's tool is using AI, and Energy Opticon's tool is also using AI on the optimization side. So here is a little quote from Kraftringen, why they think this was profitable for them. And here is another quote from the local rental housing company, LKF, who have been very successful in this collaboration together. So how does this digital platform work? So you have the production side where you have, of course, the production of heat and cooling and electricity optimized, and the load and price forecast, availabilities, and then the trading optimization. Also optimization of the forward temperature out in the heat network. And then you have to have this flexibility for the electricity up and down regulation at critical hours. And then the heat network then can be used also as heat accumulation and pre-charge it before peaks. And then you have the building side also in the optimization. And there on the building side, you have thermal control, temperature sensors, self-learning AI, and the building side is sending a day ahead flexibility forecast to the energy company to let them know how much flexibility is available from the buildings for implementation. So we built this platform on 3 different pillars. So one of the pillars were the heat flexibility, where the resource then is the heat network itself and the heat in the buildings, where you can charge and discharge the heat at optimal hours, let's say for 4 to 6 hours, without the residents noticing any discomfort. And then you have what we call the energy flex, where the resource is heat pumps in the buildings or cooling machines, which is optimized then together with district heating and district cooling, where the optimization is always using the cheapest energy source and then automatically using what is the best for the energy system. So this is a collaboration, which means that the building with a heat pump is not only using the energy company as a peak load, which in some cases became a sub-optimization in the energy system. And then you also had the electricity flex, mostly down regulation. And just the benefits with this were evaluated, and there was a proven reduction in costs and CO2 emissions. And the best part probably were also this collaboration between the energy company and the building owners. And they are now becoming more of colleagues than just these silos that I was talking about before. And they're glad to help each other and collaborate. And then also another benefit is the fault detection in the subcentrals and the automatic part of it, where everything is run automatically and controlled automatically also. And actually the indoor climate has also improved for the residents. And this solution is then replicable and scalable. I don't like that word. Okay, so, and what we also developed were business models with discounts or settlements in some cases, where you could distribute benefits for both sides, or it could be, just in some cases the discount wasn't really needed, and there was another type of settlement. It was a little bit different from different case. And then these calculation of marginal production costs and dynamic price models were a part of this. And so what is needed for this to work is these optimized production plans. They are based on price and load forecasts, and then you model the consumer flexibility in the actual energy system in a digital twin as an additional storage that can be charge or discharge for the heat flex functionality. And there, this trading market and the flexibility models is also implemented. and then you run the optimizations, and then you get first you can do like these feasibility studies to see if there is a gain, a potential gain for this type of flexibility, and then you can you get these kind of production plans for the daily operation, where the flexibility is shown also as an additional unit, so to speak. And on the production side, we're using AI for the load forecasts. So we're using machine learning and neural networks, and combine it with statistical methods also. And this gives very accurate load forecasts, which are important to have these accurate production plans also. And so a little bit about the energy flex that I was talking about, where the heat pump is installed in a building, or district cooling machine. Cooling machine, where it is kind of competing a little bit with the district heating and the district cooling from the energy company. So that's why the energy company really needed to have this collaboration because this was causing restrictions in the energy system and sub-optimization. So here we developed a very nice functionality where we could optimize on economy, CO2, and primary energy, or a combination of the three. So to find the sweet spot, so to say. And what was needed here was also calculation of marginal production costs and dynamic price models, since it was collaborating with the heat pump in the buildings, and there needed to be an incentive for the building owners to be part of this flexibility. And also the flexibility depends a lot on the volatility and level of the energy prices. And this marginal cost calculation in Kraftringen is generated by the optimization in our resolution in a very complex energy system, because this heat network of Evita is actually a connected heat network where you have Lund and Helsingborg, another city, and Landskrona. So there are actually 5 cities connected with their heat network, and 3 different energy companies are owning these facilities. So, and they do a total optimization together in one system. So this cost had to be including all the units in this Evita system, not only in Kraftringen. So, and the heat flexibility is connected to the production cost as well. And this marginal cost was then an input to a dynamic price model that was then presented to the building owners. Yes. And here are some outcomes from the test objects during these years that we tested them for the energy flexibility with a heat pump and cooler machine. And this is in percentage. And so a reduction in production costs. Actually, this financial optimization was an average of 13%, and reduction of CO2 was an average of 27% for these 4 test objects in combination. And the primary energy usage optimization gave a result of 30% reduction, which was quite nice to see. See, and here is an outcome of the heat flexibility in some buildings in Eslöv, close to Lund. And when they started and connected these systems, Energy Opticons and Noda system, you could see here that they were a little bit careful in the beginning. So the red The red parts are the discharge, demand-side management discharge, and the blue parts, dark blue, are the demand-side management charge. And so if you can see here that in this area over here, there is an increase. They started using this system more aggressively, so steering much more, and they noticed the building owners didn't notice any changes in comfort from the residents. Exactly. So yes, I give over to Christian now about customer
Yes.
engagement. Yeah.
Thank you very much. And it's actually cool, the graph you just showed here, because it was not only for the demand response we were doing this, but it was also for the optimization of the individual building. And I think that's one of the things I will just briefly touch upon here when it comes to customer engagement. We mentioned before that all these systems are demand driven. So in demand in energy systems, obviously they are the consumers. So you need to get the consumers on board, technically, obviously, but also from a business perspective, and also from a, more in general, just getting them engaged in different ways. But I think the first part of that is obviously to connect it from a technical perspective. And this is what we see here in the this graph here also, that you want to make sure that you hook up a lot of buildings. And how do you do that? That is a bit of a challenge, really. You can always connect a lot of buildings if you have the budgets for this, but this has to be done in a very cost efficient way, and make sure that we really see that we just get the appropriate amount of data and use it in a good way. And it's the scalability and replicability that Pierre was talking about before. This is really also where I think that the kind of AI solutions that we build are kind of really coming into play and shining, because this is where we need the self-learning behavior. This is where we need systems to adapt by themselves. If you have one production unit or a few production units, you can spend time on optimizing them more or less manually. But if you have 1,000 buildings, then you need to ensure that all of them are really operating automatically, self-learning, and using the data that they have available to them. And this is really where we see that these kind of technologies start really shining. And first step, get the data into the system. Here we have the 3 different levels of data access that we're talking about. Obviously you want to do it, you don't want to add more hardware. There's already controllers in all buildings. There are already BMS, building management systems, and sensors in most buildings. If this is the case, well, connect to these things. This is the first step here with the IT based. I think this is really what we're trying to push in these kind of projects. Certainly in the Kraftringen case in Lund, but also especially in the next one in Gothenburg, where there are many, many buildings. We need to use the data access solutions through IT, no hardware. But sometimes you need to add something. Then we have this modern hardware approach where we connect through different levels of automation also with the buildings. And then the last one, we have the we can actually jump back one step.
Okay, sorry. Yeah.
We talk about the legacy hardware also. This is also when, everyone here probably knows that if you go out into a lot of buildings, there will be buildings with controllers from the 90s or 80s. Nothing wrong with the 80s, 90s. Very good music from that time. But the controllers were not really appropriate for active control. And so we need to upgrade them. And this is also something we can do by, adding very cost-efficient gateways. And so there are good solutions for this also. But this is really at the core of when we want to connect buildings, we want to gather all the data. And once you get the data, this is when the fun starts. Okay, you can go to the next slide now. Because then you take the data and you transform this into information, you transform it into knowledge. And this information and knowledge, this is really where we see this self-learning behavior. This is I chose this picture because it kind of signifies what we're doing in individual buildings. We're using the thermal inertia of buildings. We're working with the quality of service within the buildings. And this is where Pia mentioned before that there are forecasts of flexibility. These forecasts are 24 up to 36 hours ahead of time. Where do these come from? Where does the flexibility come from? Well, flexibility is, you can see it as a deviation from normal behavior. This is what creates flexibility. And normal behavior is there because it ensures a certain level of quality of service. And in a building, this quality of service normally relates to the indoor climate in one way or another. What you're looking at here is just an example from a building where we're kind of building self-learning models of the indoor climate, so the system tries to learn what goes into the building, and once you control the building, what happens, the impact. And this is an interesting example. You can see that Pia mentioned forecasts on the big level, the whole network. And that's actually quite easy to model a whole network compared to modeling individual indoor climates. It's a much more volatile data set. And this is really where you want these kind of machine learning technologies. You can see here the difference between the measurement, the green line, and also the gray dots with a line also. You can see they're kind of following each other quite well. And if you look at the deviations here on the left side, on the y-axis, it's not much. This is in centigrades here, degrees indoor climate, so it's not much. Even if it looks kind of volatile now, it is within quite a small span of temperature. And what you can also see here, the gray dots here, they are a forecast. So now we can see it, once we measured over time, but they were actually created 24 hours up to 36 hours ahead. And you can see it follows when it goes up. You can also see when it follows when it drops down quite rapidly during a few hours later on during the day. And you can see that it's not entirely correct, but more or less it follows the trend very, very good. And this is kind of the core. If you can't do this, then you can forget about creative flexibility on a wider scale. Because if you can't automate what you're looking at here, then you can't scale things up. Then you can't replicate these things over large group of buildings. And this is also at the core of the thing, because if you can't ensure quality of service, then the customers will not be happy. They will not be, engaged in this. So this is we really need to do this in a good way. And this is where we see these kind of models really shining also. If you take the next slide here, please. So once you have this in the system, so the system has an understanding of what's going on in the buildings. It understands how it can model the indoor climate, and it understands if you control the building, this or that will happen with the indoor climate. So the system has this flexibility. It has the ability to calculate what's going to happen. And then this is used then to, because now we're talking about individual buildings. Now we're going to scale this up to all the buildings. And how do you do that? Well, we're using, Pierre mentioned earlier that we were using, kind of embedding this in business models. Well, this goes all the way down into how we use AI and multi-agent systems in order to coordinate this kind of behavior among all these buildings. So we're actually using, it's actually using an auction model. So mathematically, it's using an auction model to coordinate the behavior among all these software agents. Each building has a software agent. And this agent, well, it has two goals in life, One goal is to ensure quality of service, make sure that all the tenants, people in the buildings are happy. The other thing is that it wants to buy control actions, from Optima, the the aggregate optimization system wants to control maybe 5 megawatts, but one individual building can't absorb 5 megawatts. So it has to distribute this 20 kilowatts over there, 50 kilowatts over there, and so on and so forth until you have your 5 megawatts. And this is done continuously by this auction process. So all the buildings are bidding and trying to buy control actions. And the currency they're using in this auction process is deviations from their normal indoor climate. And this is why it's so important for the system to have this self-learning understanding of what's going to happen, because then the systems can automatically bid, and the currency they're using is the deviations of the indoor climate, which is calculated in advance by the system. And if they buy more and more, well, then they don't have any money left, because they spend all their currency because they're deviating too much. And that means that there's a self-balancing mechanism within this auction process, which makes it mathematically very, very nice. And this is actually how things work. And the cool thing here is also then that you can tie this to actual business models. So because you're using this every hour or every time step that you set the system to operate on, it will provide every building will, all these agents, they will get digital contracts based on what they bid in the auction, what they win. And then they say, oh, I got my 20 kilowatts. Now I'm going to control this. I'm going to provide this flexibility. And this is saved in the system as digital contracts. And this can be used in actual business models afterwards in Swedish kronas or euros, whatever you want. And by doing this, you have a self-balancing system and you have a system that can scale because it's self-balancing. And it's self-balancing in the sense that if you don't have any money, you can't buy anything. It's very simple, really, you know. And this is how this is how we get things to work, regardless if it's 10 buildings or 1,000 buildings. And then you get, you add this all up, and you add all your kilowatts up, you get your megawatts. And this is what you get a grid level or network level impact, where you can move things around in the demand profile of the whole network.
Yeah.
So this is basically how it works under the bonnet.
I don't know how much time we have left. Are we still on schedule? Okay, let's move on. I didn't really hear the reply, but so here are the basic conditions for replication. So on the building side, you need a connection. They need to be connected to the district heating network, and there have to be some type of mass in order to use this flexibility. So it can't be single houses, or correct me if I'm wrong, Christian.
It can technically be, but you know, it's the bigger the better. That's not always the case, but in this case, yeah.
Exactly. And there has to be some flexibility in the indoor temperature. It has to be connected to a control system, and it has to have communication to the production optimization. And it needs this type of AI system that Christian just explained, with this type of flexibility forecast, which is very clever in my very elegant solution. And for the energy flex, you need there has to be a double connection in the buildings, either district cooling or cooling machine, or district heating or heat pump. And it needs also a building automation system that can receive these control signals for what to use and when to use it. And then you need, of course, the digital platform that we just talked about. It can also be that there is data security. In this case, in Kraftringen, we use the data lake in order to ensure the data GDPR. For the energy companies, for the heat flexibility, to be replicated, you need an agreement with the building owners on this demand side flexibility. You also need a production optimization system. You need a variable production cost or a need to release capacity in the energy system. And for the energy flex, you need to have a variable district heating or district cooling price. You need also the communication there on the production to the production optimization. You need also background information like COPs for the heat pump and energy signatures. Could be like patterns of usage and efficiency, control conditions, etc., and a need to avoid this type of sub-optimization. Okay, so moving over to the Flexus project, which is in Gothenburg Energy. So NODA is a partner there together with Kamstrup and some other actors as well. Energy Opticon and Energy Optima 3 is optimizing the energy system, and it will be connected then to over 5,000 buildings, if I'm correct. So here in Gothenburg Energy, they have large cogeneration plants. They have district cooling from the river and from surplus heat, and they have a large heat pump also in their system. They have fossil-free electricity from wind power, solar power, and they have a large thermal storage. And they are also now connecting to this consumer flexibility, demand side management. And an important thing here is that they are in Gothenburg Energy, they own most of their own substations. So this is a difference here. They don't really need to have those business models towards the building owners. And what was the challenge here? They needed to make large investments in peak load capacity to manage both current and future demand profiles. So instead, they were looking into flexibility and active demand response and different types of energy services to create flexibility and manage these current and future demand profiles. And results were expected to be with this the proof of concept would be that they would have a prolonged lifetime of existing distribution infrastructure. They would have a lower need of investments in peak load capacity, and they would lower operational costs and CO2 emissions. And as I said, this is a huge project with 5,500 buildings in this ongoing deployment project that NODA is working on right now, together with Gothenburg Energy and Kamstrup, and collaboration and sharing and data sharing. So here is also a little quote from Gothenburg Energy about this project. I think we're running short of time, so I just want to jump into the conclusions. For the heat flexibility, it's a scalable system solution, as Christian just mentioned, which is really important. Daily production optimization with connections between the two systems, and a day ahead plan and automatic optimizations running every hour also. And it has a very high replicability potential. And of course, the profitability here depends on the energy mix of the local district heating network. But in Kraftringen's case, it was very profitable. And for the energy flex with a heat pump or cooling machine, it's a growing need all over Sweden in the Nordics, and the energy company needs to avoid this sub-optimization, and which requires also new business models towards the building owners. And the work methods, how this was done was there was first a theoretical analysis, a potential study made, and then they did a small scale pilot to validate the theory that they had. And then after this, it was an evaluation and calibration of the platform. And the fourth step, where we are right now, is the large scale replication, where the building owners are actually so positive towards this that they're standing in line to be connected to this platform. So what are the incitaments? Of course, the green energy transition and new regulations, such as from EU regulations for buildings, are creating challenges. And of course, these innovative tools for flexibility and AI, digitalization, and sector coupling are a part of this solution. And these new types of collaborations and integrations, creating these type of energy ecosystems between the energy companies, industries, and property owners can deliver real energy system benefits. So here are some of the conclusions. There are a lot of flexibility potential during large parts of the year, especially in spring and autumn, that can be used, and electricity can be released into the grid at critical hours. There is a reduced risk with double connections, and of course, increased potential with a variable electricity price. And also this cost and environmentally optimized energy supply using AI. And next steps for this work is more building owners connecting. Right now, the local municipally-owned building company is being connected with many buildings. And for the next step, we have intraday and MFRR trading modeling in this system to handle the impact that this changed behavior in the system has on the electricity balance towards the balance responsible party. So this is now being developed in this new project called Coaction Lund for a climate neutral city before 2030. So that was it from us. I hope we are still on schedule. And I hope.
Can you hear me now?
Yes, I can hear you.
Great.
Yes.
I actually had some sound problems, so sorry for that. Yeah, thank you for those great insights. And of course, it was absolutely no problem that you explained those insights a bit further, because AI is, as you have said, a very great topic and a very wide range you are covering here. So absolutely okay. I think we can now go to the Q&A session. And to start with, maybe you could elaborate or maybe summarize the methods you're using in the AI model. So did you use a proprietary AI model, or did you build one based on available open source ones? And what was the data set maybe used for the training? So organic or synthetic? So more of a specific question at the beginning.
Yeah, so maybe you can start, Christian, on the building side.
Yeah, well, I was going to say all the above, really, because I mean we're using obviously different models that we build ourselves, and there are certain proprietary model or algorithms that we're using also that we developed in-house. But we are obviously also dependent on frameworks for calculating these things. For example, when you're doing neural networks, for example, you're using PyTorch or TensorFlow, things like this, rather than building all that kind of stuff from the infrastructure from scratch. So we are using it. The same thing goes if you're doing more machine learning stuff. So there's all, doing regression models or whatever, you still use open source, or at least we use open source technology for these kind of things. So it's a balance in this. And when it comes to these AI stuff, it's not so much the models, algorithms themselves, it's how you set the parameters. That's the challenging part, really. And this is when we talk about self-learning stuff. It's not about coming up with a new algorithm, really. It's about coming up with the parameters for that particular model.
Yeah, same here. So we have also developed our own AI models, for example, in Python, and we have used various different models actually and compared them to each other. But it's mainly machine learning and neural networks on the production optimization side.
Yeah, thank you for answering that question. Actually, if I understood you correctly, Christian and Pia, it's not much the model, or it's more of the premise you are setting.
Yeah.
And this is, of course, a a good answer for all those people who are trying to come up with those models, because of course open source software has this kind of, yeah, I would say maybe this image of being free, but also being very risky maybe. So this is of course a good answer to that.
Yes, and you also have to follow the AI Act, which is
Yeah.
something that we had to investigate as well. So because of course everyone is asking that now when we deliver our systems to customer, that are you compliant with the AI Act? So
Yeah, okay.
And I
Yeah.
think this is a good point also. I mean, to have you need to combine domain knowledge and AI. AI itself is just a tool that we use to do these things. You need the domain knowledge, otherwise you're screwed. You know, it's you can't just go in there and say, well, we'll just have an algorithm and let's just see what happens. That, you know, shit in, shit out kind of thing.
exactly, yeah.
Yeah, going deeper into the business model, is the business model optimized? So the transactions, for example, or would you explain this differently?
You mean the business models towards the building owners, between
Yes.
the energy company and building
Yes.
owners? Yeah. Yeah, I'm a little bit. There are different types of building or of business models used in this system, and a basis for this was to develop this to calculate the marginal price, and then kind of have these discussions with the building owners. Where is the win-win for you? And yeah, I think. A discount was discussed. Dynamic pricing models was also used in some cases. So yeah, I'm sorry. Did I reply to your question? I'm not really sure what was the original question. Yeah,
No problem.
yeah,
If the business model is optimized.
optimized.
So,
Okay.
yes.
Yes, Christian, what would you say about this?
Yeah, it is to a large extent. And I mean, we both have models for, like Pierre is saying, marginal cost directly. So there's a one-to-one relation between cost and supply and cost at the demand side. There's also where you can look at more traditional prices for district heating. You have the kilowatt hour or gigajoule cost, but you also have a cost for demand, the kind of demand profile you have as a consumer. There's a cost relating to the return temperature. There's a cost relating to the volume that you use. So you want to have, as a consumer, you would want to have a good functioning substation and heat exchanger in order to get a good return temperature and have a good balanced demand profile. Otherwise, it's going to cost you more. This kind of built into the system so that the substations, the controllers, they will react to the price model being used in the particular network.
Yeah, thank you. You already mentioned some issues on the way to building that model. Have you observed any technical challenges, difficulties on the equipment side during the implementation, or maybe on the client side?
Well, I mean, there are also always challenges, technically, but you can solve all the technical issues. That's not a problem, really. I think the main issues that we see is really what we just talked about, the relation between people. Machines not the problem. It's
Yeah,
people
exactly.
always the problem. So
Yes.
you have to have good business relations or the contracts, how to do this. I think it's also, if you look at it from a European perspective, it's also or more rigid contractual setups that are not really appropriate for these kind of dynamic business models. And I think that's
Exactly.
something that we really need to work on, or we as
And
energy companies.
And another thing was that, yeah, exactly this communication between the two parties where they can meet. And like I think this is one of the keys to this successful implementation. And for example, some building owners, they wanted more an optimization towards environment, like the CO2 optimization. And some were more interested in the primary energy optimization, and some just wanted to optimize on cost. So being able to deliver a system that can optimize and weigh these different things or find that sweet spot was also an important part to to be able to deliver this maximum value to the building owners.
Yeah, thank you. And very interesting because I think optimization of relationships between people is actually not something that you are thinking of if you are elaborating on that topic, I think.
Yeah.
Yeah, coming to flexibility as a topic on a local level, but also on in an international dimension. What is the flexibility potential in standard households in terms of electricity consumption expressed as a percentage? Do we have some information on that?
I mean, on private household, like individual houses, or
Yeah.
we don't really work with individual houses in this project. But maybe Christian, you have more experience with the building side.
Yeah, I mean, normally if you just on average over time, it's normally about 10 to 15%. If you look at this is the kind of flexibility you would normally be able to extract, regardless if you're using electricity for heat pumps or other, HVAC stuff, or if you have district heating. This is kind of built into the thermal inertia of buildings, 10-15%. If you're talking about industrial processes and stuff like that, it might differ depending on the situation, but we're talking about buildings, 10-15% over time. And that can be like 30-40% short term, but long term, 10-15%.
Yeah, thank you for this precise number. Yeah, coming to the international dimension, in the energy flexible ecosystem that you've shown, how complex do you see the metering and settlement arrangements? And this is where this sort of complex optimization can struggle in the UK markets, according to a participant of this webinar.
Yeah, the metering in terms of GDPR, or what type of difficulties, like metering the data access, or what type of
Maybe you can start with that, and the participant who posed that question can maybe elaborate on that in another question.
yeah. Yeah, that's also a question to you, Christian, I think, because you are also an expert on the building side.
Yeah, I mean, I think the UK have their special challenges in general. And one of the things is how you connect buildings. So I think this also comes back to what I mentioned before with rigid contractual setups and policy, schemes. We are involved in a few projects now in the UK, for example, in the Heatropolis project in King's Cross in London, where there's sector coupling going on between district heating locally and also the surrounding power network or power grid. And this is something that we're actively working on also now. And I think in that particular project, we're going to review a set of different district heatings and how they can connect to the power grid and interact through heat pumps or combined heat power. And one of the things that we're looking at is actually what was just mentioned here. How do you actually build this from a business perspective rather than just the technology? We have the technology, but how does it work in that particular context of UK in this case? And I think it's very much district heating can be used as a kind of a buffer for the power grid in that case. And I think that's kind of the overall take.
Yeah.
In that project we had the UK PN, who's the kind of primary owner of the project.
And I think also another, I mean, there are challenges to develop these business models which are unique for each country. Like I know in France, like when a building is being built, there is sometimes a contract that says that it has to be connected to the district heating company and has to take. So there are always, you have to look at the local market and see like where are the potentials? Is there any potential here? I know in Germany there is like this GDPR on the building side is something that many mention could be a challenge for these type of solutions. But there are always ways to handle this, anonymizing data, and yeah. So
It's interesting you say that when it comes to Germany. One way that we're doing it in Germany is instead of we avoid the trouble of going all the way into the buildings. We optimize the network stations. It's quite common in Germany that you would have kind of network stations rather than inside the buildings. You have like subnets, and then you can optimize these things because they're already owned and operated by the network operator. So that's one. It's the same technology, but rather than going into the buildings, you stay at the network level. So you can still do these things.
Yeah, very interesting that it's so dependent on the local market, of course. So I think the answer to that question would be to look at the local market and then decide how to cope with that. Yeah, maybe covering two last questions, maybe. Christian, can you maybe give more information regarding the customer engagement that you elaborated on how the agents were implemented in the virtual auction?
How they were implemented? Well,
Yes.
I mean, it was basically implemented as a multi-agent system. So each agent, it's self-contained software that needs to, enforce their own goals. In this case, as I mentioned, the quality of service and also engaging in this control scheme. So it's basically based on a multi-agent system without, going into more details here and now. I can elaborate at great length about this if you want. I wrote a book about it actually, and but let's not do it here and now.
Yeah. Yeah, thank you for this short insight. I would say this sounds very complex if you have multi-agents with their own software, of course, and all this has to be integrated. So I think an answer to that question would be it was implemented in a very complex way, and with not just one software, but with more than one software. Regarding the customer engagement and maybe also customer satisfaction, you talked about the building owners. In addition, what about the people living in these buildings? Were they satisfied?
Yes.
Did they have to change their behavior, or
Yeah.
was all optimization done by the system?
Actually, that the building owners were a little bit scared in the beginning that the building residents would complain. But when we started using this system, there was actually no complaints at all. And it was even an increased in satisfaction. So the building owners told the energy companies that you can start using this more aggressively. It hasn't at all affected the indoor climate in a negative way for the people living in the buildings.